Regioselectivity of the cycloaddition reaction is a very important topic, and very few students have clear understanding of this particular topic, and very few teachers will explain you with clear explanation and logical explanation, right? So in this video I will discuss about all the explanation of the regioselectivity of different type of cycloaddition reaction, and in addition to that I will also give you the shortcut by which you can solve the problems very quickly. So welcome to Chemistry Lover, and let's start today's topic. So you can see these are the all possible cycloaddition reactions, not actually all possible cycloaddition reactions, but these are the most common cycloaddition reactions. One is 4+2 cycloaddition reaction in thermal condition, which is the Diels-Alder reaction. The second one is the 2+2 photochemical reaction, and the third one is 2+2 thermal cycloaddition reaction. Okay, so these are the three main classes of the cycloaddition reaction, of which you have to bother about the regioselectivity, right? Now I will discuss what are the factors that govern the regioselectivity of this particular reactions, and for that you have to consider 3 points. Number 1 point is which are the important orbitals that involve in the overlap in the transition state, right? So what are the important orbitals? The second point is the coefficient of the orbitals on different carbon atoms, and the third point is the extent of the overlap of these different orbitals in the early transition state. Okay, so I will discuss these 3 points for each of this class of the reaction one by one and make you clear about the topic, and also I will tell you the shortcut by which you can solve the question very easily. So first let us consider the case of 4+2 cycloaddition reaction. Now before discussing that, one thing I want to tell you is that, so I presuppose that you know the basics of the cycloaddition reactions, and then I proceed because I will not discuss about the basics of the reaction. I take that you know the basic mechanisms. Okay, so if we take any cycloaddition reaction of 4+2 cycloaddition reaction, that is Diels-Alder reaction, you know this is the general description of a Diels-Alder reaction, where this is your diene and this is your dienophile. They react to give you this cyclic compound. This is why it is a cycloaddition reaction. Now the general orbitals or the common orbitals which involve in the overlap is the HOMO of this diene. This is the HOMO of this diene, and the LUMO of this dienophile, right? Now if your diene and dienophile both are symmetric, then you will see the coefficient of this HOMO will be same. The shape or the size of this HOMO will be same on this carbon 1 and carbon 4, so there will be no difference. So this is how the HOMO will look like, and then if your dienophile is also symmetrical, then their coefficient will also be same, and they will overlap to do the reaction, right? But when you have substituents like this, for example here you can see in one side there is a OMe substituent which is electron donating group, but in the other side there is no substituent. Like similar cases here, you can see in C2 there is a substituent OR, but there is no other substituent in this place or this place. So when this substituency there are, for example in this case this is the dienophile, and here again you can see in one side there is a electron withdrawing substituent, in this side there is no substituent. So when substituent is there, the coefficient of this HOMO or this coefficient of this LUMO, they will differ on these different carbon atoms, and you have to determine which carbon atom will have higher coefficient. Now because in the early transition state, so now what is mean by early transition state? So we also represent the Diels-Alder reaction by the Curly mechanism like this. Okay, and now we say that this is how the transition state will look like. So when you have symmetrical diene and dienophile, the extent of this bond formation will have similar effect on both of the sides. So in the transition state, both of these bonds, this carbon atom and this carbon atom and this, they will have same bond formation, right, in the transition state. But when you have unsymmetrical case, then this bond formation will not be same, right? So in one side the bond formation will be faster than in the other side. So in the transition state there will be, so in the early transition state there will be bond formation from one side, whereas the other side may not have yet started the bond formation, right? So for example, let's say you have a case where you have higher coefficient of HOMO on this side and lower coefficient of HOMO on this side. So by the size of these lobes you can understand that this has higher coefficient of HOMO, this has lower coefficient of HOMO, right? And now let's say this is the LUMO of the dinophile. So let's say it has higher coefficient of LUMO and it has lower coefficient of LUMO. So in the transition state, this side bond formation is started, but this side yet the bond formation is not started. So the transition state will look like this. Okay, so the transition state will look like this, and here you can imagine a delta plus and here you can imagine a delta minus, because this is the HOMO. So electron is flowing from HOMO to LUMO, so it will acquire a positive charge and it will acquire a slight negative charge. So this is how the transition state of an unsymmetrical dyne and dinophile case will look like. Okay, now all the regioselectivity which comes from this particular case is dependent on the stabilization of this positive charge and negative charge which we can imagine. So now we have to understand that how we can determine the which carbon atom will have higher coefficient of HOMO or which carbon will have higher coefficient of LUMO. So for that there is a very simple rule. For example, we take this case. Here you have electron donating OMe group. Now how can we determine which carbon atom will have higher coefficient of HOMO, whether carbon 1 or carbon 4, so C1 or C4? So for that the simple rule is think about the reactivity of this particular compound with any electrophile, for example bromine. Okay, so any electrophile you can imagine. In this case we take bromine, so the HOMO of this dyne will react with the LUMO of this bromine, which is nothing but the sigma star. So we know that the reaction will take place like this. Okay, so we can see the reaction will take place like this. Here you will have a bromine and here you will have a OMe, right? So positive charge. So you can see from this side the reaction occurs. If you do from the other side, that is if you push the arrow in the reverse direction like this, okay, so if you do it, you can see from here. So the carbocation which will be formed here cannot be stabilized with the lone pair of this oxygen, so that's why this will not take place and this will take place. So from that we can understand the HOMO has greater coefficient on this carbon atom and lower coefficient on this carbon atom. So this carbon atom will have lower coefficient of HOMO, whereas this will have higher coefficient of HOMO, right? Similar is the case with this. So you can see, if you imagine the reaction of this, you can see this is how the reaction will occur, not from here. So this is wrong, this is right. So that means this carbon will have a higher coefficient of HOMO and this will have lower coefficient of HOMO. So this is how you have to determine which carbon will have higher coefficient of HOMO and which will have lower coefficient of LUMO. So for determination of the coefficient of HOMO, you have to imagine the reaction of that HOMO with any electrophile. Now how can you determine the coefficient of LUMO? So for that you may get the point that in this case we have to look into the reactivity of that LUMO with a nucleophile. For example, if you take this case, so here you have OR, so any nucleophile if you add, that will attack on this position to give you this, because that will give you the stabilized carbanion, right? So this is where the nucleophile will add, and this is wrong. If you add the nucleophile here and generate carbanion here, so this is wrong because the carbanion cannot be stabilized into this carbonyl group, so this is wrong. So your LUMO will have higher coefficient over here and lower over here. Now the point is very clear. So the point is very clear, and you can see this will be the correct alignment of the reaction. So this is what the correct alignment is, and you will get this product OMe. Here you will have COOR. So this is the product you will get, and not this. So this is the wrong product. This is the wrong product. Another way by which you can look into this is, you can see in this particular case, so we know that it goes through a aromatic like transition state, right? So it goes through aromatic transition state like this, and in this aromatic transition state, this electron donating group and this electron withdrawing group, they are placed ortho to one another, with respect to ortho to one another. In this case it is meta, so meta is wrong. It has to be placed ortho with respect to one another, right? Now let us take the case of other example. So here you can see this is the other example where you have this, here you have OR, and we said that it will have higher coefficient of HOMO, it will have lower coefficient of HOMO. Whereas for this case where you have NO2 group, now you can see this carbon will have higher coefficient of HOMO. So here you will have here you will have higher coefficient of LUMO, and here you will have lower coefficient of LUMO. So you have NO2 group. So NO2 is also electron withdrawing. So the case will be same for this and this. Now if they overlap, you will have a product like this, OR and NO2. So again you can see they are para to one another and not meta. So either they should be ortho, so electron donating and electron withdrawing group should be ortho with respect to one another, or para with respect to one another, but not meta. So this is how you can easily determine the regiochemistry of whole plus 2 cycloaddition. So the shortcut is, by looking into the reactivity of the ionic reaction, you can determine the coefficient of HOMO, and according to that you can do, or the very simple shortcut is, you just think the pericyclic reaction as some ionic reaction. So what you can do, you just think it is an ionic reaction, and in case of ionic reaction, what it would do, so it would just attack like this. So this is the perfect mode of attack. So here you will have plus, and now you can see, you can imagine enolate. So this is not the actual mechanism, but for shortcut you can think like this. Now it will give you the desired product, right? So you can think it like ionic mechanism, and that will save your time. You can easily solve this. Same is the case with this. You can try it with yourself, or also you can think of ortho para orientation. So this is the case of 4 plus 2 thermal cycloaddition reaction. Now let us see for this 2 plus 2 photochemical cycloaddition reaction. Now in case of photochemical reaction, you know that it is not the HOMO-LUMO interaction, but it is either the LUMO-LUMO interaction or HOMO-HOMO interaction is important, because it goes through the excited state, right? And again you have to determine the coefficient of HOMO and LUMO. Now in this case, the coefficient of HOMO and LUMO will be just, coefficient of HOMO and LUMO will be same, but here you can imagine, for this particular case, if you consider this and if you make it react with any electrophile, it will attack from this side, because that will give you the tertiary cation, right? So that means this particular component, it will have higher coefficient of HOMO over this and lower coefficient of HOMO over this. So this is the coefficient of HOMO for this, and it will react with another molecule of this, but with HOMO, not with LUMO. So for photochemical case, HOMO-HOMO reaction or LUMO-LUMO reaction will take place. So then it will react with the same molecule, but this orientation, because now the larger lobes can overlap, because if you turn it, then this larger lobe has to overlap with this smaller lobe. So the reaction will take place like this to give you this product. So this is the correct orientation. Now for this particular case, you can see again, so you can see this will be the highest coefficient of HOMO, and for this particular case, so we have seen that in case of LUMO, the highest coefficient was over this carbon. So for HOMO it will be just reverse. So for HOMO you will have higher coefficient over here where you have the electron withdrawing group and lower coefficient over here, right? So this is homo, both are homo, so it is also homo, and now it will give you this product. Okay, so actually this is COR. So this is the product you will get. Now you don't have to think much about this homo and lumo. So what is the shortcut then? So the shortcut is, you can see, if you consider the reaction as ionic, what you would do. So if you consider the reaction as ionic, you would do like this, because you can see by this you can have the correct intermediates. For example, you will have the enolate where the negative charge is stabilized into the carbonyl group and positive charge will be on the secondary carbon. So if you consider this as ionic reaction, this would be your product, right? So this would be your product, but we have seen we don't get this product, we get the different product, that is these two are these two different side. So now what you have to remember is that for the photochemical case you have to do the reverse what you have done for the thermal case. So for the thermal case you thought the reaction is ionic and accordingly you did the reaction, but in photochemical case you have to do the reverse. So if you do the reverse, what you would get? You would get this product, because it is not thermal reaction, it is photochemical reaction. So take this thing in your mind that for thermal reaction you have to imagine the reaction as ionic, but for photochemical reaction you have to do the reverse. Now the last topic and the 2+2 thermal cycloaddition reaction. This is the most vital topic and people just don't understand this very clearly, so pay full attention to this. Now in this case you can see, so first of all this reaction only happens with this ketene and not with simple alkene. So only ketene can do 2+2 cycloaddition reaction. Here you can see it is a diene and you can also consider it as a dienophile, but still it gives the 2+2 cycloaddition reaction and not 4+2. So this proves that 2+2 is faster than 4+2. Now the reason behind that may be the orbital energy matching. So maybe the dienes homo and its lumo, their energy is too high when we consider their energy gap is too high when we consider a 4+2 reaction, but in 2+2 reaction it may be low, or the extra orbital which is present at this carbon atom, that may be the additional factor. We don't know the exact reason, but the conclusion is that with ketene 2+2 reaction is much faster than 4+2, because if you do the reaction of this diene with some ordinary dienophile, for example NO2 group over here, you will get clear 4+2 reaction, but when you do the reaction with ketene you always get 2+2 reaction. So that means 2+2 reaction is ketene is always faster. Now let us come for the regiochemistry. So again it is a thermal reaction and that's why you can consider the reaction as ionic and you will get the correct outcome. For example, so you can have two arrangement, either this Cl this, or you can have another arrangement like this. So this. So now what will be the case? So in the first case you can see you will have a product like this. So here you will have this product, and in the second case you will have the product like this, and you can see these two products are different because this diene part or this double bond is not symmetric. It's one side has this double bond, in the other side is saturated carbon, so that's why you can have these two cases. Now what will be the favored case? So again you can consider it as a because it is thermal reaction, so you can consider it as an ionic reaction, and if you consider it as an ionic reaction, in this case what happens? So the homo will have higher coefficient on this carbon atom and not on this. So you can see the reaction will always take place from this side. So if the reaction takes place from this side, so you will have negative charge over here, right? So, or you can imagine if you push the electron over here and attack over here, so it can open to give you a intermediate like this. So you can have a intermediate like this, Cl, and you can imagine the reaction like this. So in the next step, this O minus back and it attacks over here to give you this. Although this mechanism has no evidence, it is just an imagination, it is a shortcut, it doesn't have any correlation with the reactivity, but it will give you the correct outcome. It is a shortcut. Now it will give you this product. So now in this particular case, you can see if the attack take place over here, so your negative charge will be over here. So you can see this will be the intermediate. Now here you will have a positive charge, and here you have 2 chlorine, the negative charge over here, and this is your carbon. Now you can see this negative charge, it doesn't have any stabilization over this oxygen because it is on this carbon atom, whereas in this case you can see it has a stabilization over this oxygen. So oxygen negative charge stays on oxygen, which is more electronegative than carbon. Here the negative charge stays on this carbon, which is less electronegative than oxygen. So that's why this anion will have much more stabilization, and now the attack over here will give you this product. So you can see this attack is much more favorable because it gives you more stable anion, right? So this is the correct regioselectivity of the reaction, or correct the correct regioselectivity of the reaction, and you will get this as your correct product. So let us discuss the another example which we have. So the another example is this one, and you can see the same logic you can also apply here. So now you can see, so of course you can see now the attack will take place from this side, and we know, so this should be our orientation. So here you will have methyl groups, and if the attack take place over here, so you will have like this. So in the first step you will have this, you can see this is the tertiary carbocation, and you will have, so basically we can just rotate the structure. You will have like this. Okay, so here you will have 2 methyl group, and when this oxygen come back, it will attack over here. So from this you will get this product. Here you will have oxygen, here you will have 2 methyl groups, and here you will have another methyl group. So this will be the correct product, and this is the regioselectivity. Now the same thing we can explain with the homo-LUMO interaction also. So but in this case this is slightly different. The homo, so for any ketene, if this is your ketene, the homo will have the highest coefficient on this carbon atom, right? Homo will have highest coefficient on this carbon atom, and the LUMO will have highest coefficient on this carbon atom, and they are not in same plane. So this is very important. So let's say this is the z axis, this is the z axis, so then it will be, let's say, along y axis. So just let's say this is our coordinate, this is our z axis, this is the x axis, and this is the y axis. So if your homo is along the z axis, then your LUMO will be along the y axis, right? So this is the LUMO and this is the homo. So you can see if we consider the homo of this, so it will attack on LUMO of this compound, right? And for this particular compound, the LUMO is this. So LUMO has highest coefficient on this carbon atom, the middle carbon atom, and here the logic is same, that this attack is taking place on this carbon atom, the middle carbon atom. So this can be also explained with this homo-LUMO interaction, and I am not going deep into this because it is a very vast topic and beyond the scope of explanation on this particular video. But if you just remember this shortcut, it will help you a lot. So this is the whole thing, and if you just understand these things, the explanation, you can solve any question regarding that. So thank you for watching and subscribe my channel.